All right, so let's get started. So I've got a spring block system compressed by delta x naught. It is frictionless till here. It is frictional from here, from this origin, from equilibrium position. It is frictional surface, where coefficient of friction is mu. All right, I have to determine the distance at which it will stop. I compress it by delta x naught and release it. What happens? There is some energy stored in the spring, potential energy stored in the spring. As I release it, because it's frictionless, there is no loss of energy here. This potential energy gets converted completely into kinetic energy till it reaches this equilibrium position. It will achieve a maximum velocity v naught. Once it crosses this, because of friction, there is dissipation of energy. There is a leakage of energy. This v naught, this energy is lost, and kinetic energy eventually becomes zero. It will stop at certain point. This distance is what I have to find out. So, how do you think we should do? Look at this, students. Let's see what's happening in terms of forces. Force due to spring is towards right. Particle is accelerating from zero to v naught. Once it crosses this line, equilibrium position, its frictional surface, velocity of a block with respect to ground is towards right, friction will be towards left, and that's kinetic friction. So force due to kinetic friction is towards left. That means acceleration is also towards left. Velocity is towards right. So particle is retarding. It initially retarding becomes velocity becomes zero. Once it becomes zero, it stays there itself. Friction disappears. No force on it. No force and velocity zero means it stays over there. State of uniform rest is attained and it stays there forever. So let's find out the distance in terms of accelerations, in terms of forces, by force method. All right, let's do energy method itself. It's shorter cut. So what kind of kinetic energy you get? I get over here half m v square is equal to half k delta x naught square. Now this is lost. Half k delta x naught square is lost in friction mu mg x, and it is equal to zero. So this energy, initial energy is half k x delta x naught square, which is lost due to friction, and final energy is zero. All right, there is no kinetic energy remaining. And where is kinetic energy term here? Not required because initial kinetic energy is zero. Initial total energy is half k delta x naught square, and loss due to friction is minus mu mgx is equal to zero. Required is x, and this is k naught, that is mu. So I'll have x is equal to k naught delta x naught square by 2 mu mg. All right. Is that clear? Check if this is correct. I could be wrong in this. Check if this results in this. Is it correct? Or should I check? This is equal to 0. This x is comfort. Yeah, that's right. Okay. Now if I ask you, given this is x naught, all right, let's say this is x naught. Find the velocity when x is less than x naught. How do I do in that case? What is the kinetic energy or what is the velocity of the particle when x is less than x naught? That means it will have some velocity when x is less than x naught. This is total is x naught. When x is less than x naught, it will have some velocity. I have to find out that velocity. So how do I do that? Velocity at origin is how much? Half k delta x naught square is equal to half m v naught square. Half gets cancelled out. V naught is equal to root k by m into delta x naught. This is my velocity at origin. This is initial velocity. I want final velocity v with a retardation of minus mu g. I can do it using kinematic equation, which is v square minus u square is 2as. So let's do that as well. V square minus v naught square is equal to 2 mu g into x. So v is equal to v naught square minus 2 mu g x under root. That's what I get using kinematic equation. I should get the same result using energy equation. All right, I can substitute v naught square to be this one. I can plug v naught over here. That's not an issue. But now let's get that using energy equation. So what is the initial energy, initial total energy? Half mu naught, half k naught, delta x naught square minus mu mgx. This is the energy lost. Total energy, initial total energy minus energy lost is what energy is remaining now? Half m v square. All right. All I have to do is substitute k by m here. I'll get m gets cancelled out. No, m comes over here. 2, this becomes 2, and this 2 gets half gets cancelled out. So I'll have v square is equal to k naught by m delta x naught square minus 2 mu gx. So v will be equal to root of. So this is energy. Whenever acceleration is not required or whenever time is not asked, go for energy method. That's faster, quicker, and less mistakes are committed in that. All you have to do is energy conservation. Initial energy is equal to total initial energy is equal to total final energy. Initial total energy is half k delta x naught square. How much energy is lost? Minus 2 mu mgx. What is the final total energy? Half mv square. Just equate all these. Difference of these two and final energy is half mv square. Equate these two. What you get is v. Required was v. All right. Okay. Now in that case, friction was only available, friction was zero between when the spring was being relaxed. Once the spring was relaxed, this from zero, from origin, from equilibrium position, there was friction. But now let us say that friction throughout. Okay, before that, let's do another problem. I project a particle velocity v naught. There's a spring here. This is frictionless surface, mu equal to zero. Friction coefficient over here is mu. There is friction till this equilibrium position. Once that compresses, there is no friction. All right, I have to understand the motion. I have to find out point where this particle stops. Initial distance is x naught. I have to find out the compression in the spring and point where it stops. So how do we do? Again, what is the total initial energy, kinetic energy? Half m v naught square minus work done due to friction, mu mg x naught. That results in final compression. When it gets compressed, velocity is zero. And total energy over there is half mu, half k naught delta x naught square. Required is delta x naught. All right. For that to be compressed, first of all, this should reach that point. That means my half mv naught square should be greater than mu mgx. So first of all, this should have sufficient energy to overcome this friction, the loss due to friction. Then there will be some energy remaining here. Only then spring gets compressed. Once the spring gets compressed, it gets compressed and then it bounces back because there is no friction here. It will again come back here with the same speed. Our speed నుంచి మళ్ళీ it will continue అవుతుంది. So it stops somewhere here, let's say, or so anywhere here in the backward journey. So what is the first compression in the spring? What is the compression in the spring? This equation gives me compression in the spring. So this 2 goes off. This becomes 2 here. So delta x naught is equal to m naught square by k naught minus 2 mu mgx naught by k naught under root. All right, nothing. See, here is my energy equation is done. This is just manipulation. I'm just simplifying the equation. I'm just isolating delta x. I'm making delta x not the subject of the equation. All right, so physics is done over here. See what's happening basically. If kinetic energy is sufficient enough to overcome this loss due to friction, the spring will get compressed. How much will it get compressed? Final energy, final kinetic energy of this particle is zero. So initial energy minus the loss results in total energy, total final energy. What is the final total energy? Kinetic energy is zero. So I'll just have spring potential energy, which is half k naught delta x naught square, where delta x naught is required. That's it. I simplify this further, I'll get delta x naught. But now the question is still not over. I have to find out where it stops. So for to find out that, see whether the spring gets compressed or not, the energy over here will be the same as while hitting the spring. It's, let's say it's V. When it comes back, it's again V, right? Because there is no loss in this region. There is no loss in this region. There is no loss in this journey. By compress అయినప్పుడు మళ్ళీ రిలాక్స్ అయినప్పుడు there is no loss of energy. So ఎంత ఎనర్జీతో వెళ్తుంది అంత ఎనర్జీతో ఇలా వస్తుంది. So this is same as So length length required for it to totally stop is half mv square is lost in friction minus mu mg x equal to 0. So x is equal to, m gets cancelled out, v naught square by 2 mu g. Now this is the total length that is traveling for it to dissipate the initial kinetic energy. Initial kinetic energy లాస్ట్ లో వెళ్ళి మరి ఫైనల్ జీరో రావడానికి ఇంత ఎక్స్ ట్రావెల్ చేయాలి. ఎంత ఎక్స్ ట్రావెల్ చేశారు యాక్చువల్లీ ఎక్స్ నాట్. సో వాట్ ఇస్ ద రిమైనింగ్ ఎక్స్? రిమైనింగ్ ఎక్స్ వుడ్ బి ఎక్స్ మైనస్ ఎక్స్ నాట్. సో రిక్వైర్డ్ ఆన్సర్ ఇస్ ఎక్స్ మైనస్ ఎక్స్ నాట్. సో v naught square by 2 mu g minus x naught is my answer. All right, I repeat the question. పార్టికల్ ప్రొజెక్ట్ చేశారు, ఫ్రిక్షనల్ సర్ఫేస్ ఉంది, ఈక్విలిబ్రియం తర్వాత నుంచి ఫ్రిక్షన్ లెస్ ఉంది. సో స్ప్రింగ్ కంప్రెషన్ అండ్ రిలాక్సేషన్ ఇస్ హ్యాపెనింగ్ ఇన్ ద రీజన్ ఆఫ్ ఫ్రిక్షన్ లెస్ సర్ఫేస్. సో ఎంత కంప్రెస్ అయితే మళ్ళీ అంత రిలాక్స్ అయిపోతుంది. ఇఫ్ ఇట్ హిట్స్ ద స్ప్రింగ్ విత్ వెలాసిటీ v, ఇట్ విల్ రీబౌండ్ ఫ్రమ్ ద స్ప్రింగ్ విత్ వెలాసిటీ v. సో ఈ పాయింట్ దగ్గర b ఉంటుంది. సో ఐ హావ్ టు ఫైండ్ అవుట్ టోటల్ డిస్టెన్స్ ఎంత ఉంది స్టాప్ కావడానికి. half mv square minus mu mg x, where x is total distance it takes to stop, is minus mu minus loss is equal to 0, because final energy is 0. I'll get total distance traveled for it to stop before stopping. So where does it stop from equilibrium position is enta ante this total distance is this plus this. I just have to find out this one. So how much is that? X naught plus question mark is equal to capital X. So question mark is equal to capital X minus X naught. Ante, that's what I'm doing here. So question mark is X, capital X minus X naught. I get the required distance where it stops. All right, now let us say మొత్తం frictional ఉంది. Now this is complicated. If you have understood this, I'll go for a complicated case now. ఇది ఇక్కడ వరకు frictional ఉండే, ఇక్కడ ఇది frictionless ఉండే కదా. Now let's say everything is frictional surface. Whole of the surface is frictional surface. I have to find out the compression in the spring. And I have to find the condition that I have to find the compression in the spring and the condition that after compression it doesn't bounce back. All right, I have to find the condition between V naught, X naught, mu, and everything, all the parameters, such that it doesn't bounce back after compression. Compress అయిన తర్వాత it should not bounce back. ఇక్కడే ఉండాలి. That will happen only when, think when will that happen? Do you understand the question? I project the particle with V naught. It goes over here, hits the spring, further compresses. Energy loss due to friction is throughout the surface, throughout the journey. when it gets compressed, ultimately, let the compression be delta x naught. So force be because the spring is k into delta x naught, k naught into delta x naught, and the friction that time will be static. And if that friction, limiting value of friction is more than this k delta x naught, then this will remain at rest. That means friction will be sufficient enough to counterbalance k delta x naught. Then it will remain at rest. What is the limiting value of the friction here? Mu mg. So my ultimate condition should be k naught delta x naught force due to spring should be less than or equal to mu mg. Alright, this is one condition for the particle to remain there itself. It should not bounce back. If it is greater than this, friction cannot counterbalance this spring force, will start coming back. All right. So let's see what is the equation, energy equation I write. This is the equilibrium condition. For that particle to be stay there, for particle to stay there itself after it comes to rest, this is the condition. How do I get this condition? From FVD. From equilibrium condition, I get this condition. Let's write the energy equation now. Energy at this point A, energy at this point B. So half mv square minus mu mg into x, where x is, all right, x, let's say this is x, is equal to half k naught delta x naught square. Now look at this from geometry, x is equal to x naught plus delta x naught. X is equal to x naught plus delta x naught. So I'll write half goes off here, this becomes 2. mv square minus 2 mu gx x naught plus delta x naught equal to k naught delta x naught square. Or this is half, this is half. I'll get delta x naught from here. I got a quadratic for this equation. You'll have one as negative, one as positive. Yeah, you'll have one root as positive, one root as negative. Yes, is it so? Yes, yes, you'll have one root as negative. How can I say that? K naught delta x naught square plus 2 mu mg into x naught plus delta x naught minus mv naught square equal to 0. I've got C to be negative, A to be positive, minus C by A. Sorry, C by A is product of roots, which is negative. So I'll have one root as negative and one root as positive. Handwriting is illegible. I'll write it neatly. Okay, that's it. That's the equation, students. I have to solve for delta x naught from here. And other condition would be k delta x naught should be less than mu mg. Is it clear?
Sir, can you explain once again, sir?
Sorry, Vignesh, you said something?
Sir, can you explain once again?
Sorry?
Can you explain once again, sir?
Okay. Okay, sure. See, there's a frictional surface. ఇంతకు ముందు ఏం చేశానంటే till here there was friction, here there was no friction. So there was no friction beyond equilibrium position of the string. ఇక్కడ ఒక friction ఉండే. So in that case, what happened? It retarded till here. After that, spring got compressed, retarded further. Spring got relaxed again. It will come to this position and then stop somewhere here. But in this case, I want this particle to stop exactly over after the spring gets compressed. Spring compress అయిన తర్వాత లాస్ట్ మూమెంట్ కి అక్కడ ఆగిపోవాలి. That's the condition I have to find out. Alright, that's the condition I require, such that the spring, once gets compressed, the particles should stay there itself. It should not bounce back. Spring మళ్ళీ relax కావద్దు. That will happen only when you have friction over there, and there is friction over there. అక్కడ friction ఉన్నప్పుడు, if I draw the FBD of the particle, this is K naught X naught, delta X naught, force due to spring, friction will be towards right, where limiting value of friction is FL is mu mg. If this K delta X naught is less than mu mg, limiting value of friction, then it will stay there. If this is beating this force, friction cannot self-adjust anymore. It will reach the limiting value. It will reach the limit. It cannot self-adjust anymore, and this particle will start moving towards left. So for it to stay there itself, the condition from FBD comes from equilibrium condition. What we get is K delta X naught should be less than equal to mu mg. All right, is this understood, Vignesh?
Yes, sir.
Okay. Now that is one condition. Other condition, other equation get from energy equation. Initial energy is half mv square kinetic energy. Loss is mu mgx. What is remaining is
Half mu m
half k string energy, string potential energy. But what is x here? X is the distance traveled from initial point to the end point. అది x అనుకుంటే x naught plus delta x naught is x. I substitute that over here for x as x naught plus delta x naught. That's it. I get the equation. I get these two conditions. That's the condition for particle to not bounce back. If at all I have to find out delta x naught, the root of this equation is delta x naught. All right. Okay. Now let's go. Is it okay?
Yes, sir.
Okay. Okay. There is one standard problem. All right. Very standard problem. It's usually done everywhere. I've got horizontal surface and it's like this. Coefficient of friction over here is mu. This is all is frictionless, but here the friction coefficient is mu. All right. I project a particle from here with velocity v naught. This height is h1, h naught. I have to find out the point where it stops from here. It is origin. I have to find out the distance where it stops. I have to find out x, where it ultimately stops. Why does it stop? It has got some energy here, kinetic energy. It will go there. It will try to rise to this level. If it can go to this h naught, fine. Otherwise, it will come back again to the same velocity v naught. I mean, reverse velocity v naught, the same speed v naught. But if this is sufficient enough to climb the hill, it will reach this point with some velocity. After this point, there is a retardation of the particle because of mu mg here, kind of friction over there. It retards eventually and comes to stop. Once it comes to stop, friction disappears, force disappears, velocity is zero, it stays there itself. I have to find out where it stops. I can do this using kinematics as well, but energy is simpler. Whenever acceleration or time is not asked, go for energy method. All right. So how do you think we should do this? So initial total energy is half mv square. I take this as reference level for gravitational potential energy. Because gravitational potential energy is zero. Now that is equal to half m v square. I want to find the velocity over there, just in case. I mean, just as an exercise, I want to find the velocity over there. Half mv square plus mgh naught. Why is it mgh naught? Because gravitational potential energy, rise in gravitational potential energy is mgh naught. This is zero level. I've taken this to be zero, so this is mgh naught. So energy over there is mgh naught. So initial total energy is kinetic energy plus potential energy is equal to kinetic energy plus potential energy. Initial kinetic energy plus potential energy is equal to final kinetic energy plus final potential energy. All right, I'll get the velocity at point O. M gets cancelled out. I'll get V is equal to V naught square minus 2gh naught. All right. If at all you want, if at all speed is asked over there, but speed is not asked. What is asked is I have to find out the distance x. So in that case, I don't even have to write this equation. I'll directly go for initial position and final position. Initial configuration of the system, final configuration of the system. Initial configuration name on the half m v naught square is equal to mgh naught. But look at this, students. Half mv square is initial kinetic energy. But by the time this goes from there to there, how much is lost? Mu mgx is lost. So loss, initial energy minus loss is equal to final energy, which is mgh naught. So I'll get loss. I need x from here. M gets cancelled out. So x v naught square minus gh naught. Yeah, simplify this and find out x. M gets cancelled out. This goes there, that comes here, gh. So v naught square minus 2gh. Is this correct? Just check if it's correct or not. I could be wrong in this. Initial energy minus the loss is equal to remaining energy. What energy is remaining here? And what is the remaining energy? Final kinetic energy is zero. Final energy is potential energy. So I'll have mgh naught, which is, so this energy is being converted to potential energy, and there is a loss of energy because of friction. So initial energy minus the loss will be equal to final potential energy.
Yes, sir, you're correct.
Is right?
Yes, sir.
Okay, now I'll send a question to you. Let's solve the problem. Yeah, look at the problem, students. It's a nice, interesting problem. He says there is a pulley block system, but if at all you want to solve a simpler case before that, let me know. Or let's go for directly go for such a case. We'll go for that. Or if you want me to solve a simpler case, we'll do that. What are the masses given? 4 and 1. If this descends by x, this moves by how much amount?
So
If block 1 descends by x, how much amount does the block 4 kg move towards right?
so 1 minute. So if block 4 is most right side, the block 1 will be acceleration will be x by 2.
Uh-huh. So if this is x, how much is that? Yeah, you're almost there, Vignesh. You're right.
Uh, 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 uh,
Sorry. If this moves down by x, that will move by 2x. That's it.
uh, so
All right. So how much is the drop in gravitational potential energy? mgx minus the loss, which is mu mg, mu into m1 m2g, m1g, m2g into 2x. Now this is equal to the gain in kinetic energy, half m1 v1 square or v0 square. If this is v0, this will be 2 v0 plus half m2 2 v0 square. Everything is known except mu. Do you understand this equation? This is potential energy drop, loss, whatever remains, that is equal to gain in kinetic energy. All right. Drop in potential energy is equal to gain in kinetic energy, but there is a loss due to friction as well. So everything is known except, okay, let's solve it. So gx minus mu 4 mu g into 2x is equal to half 1 v0 square by 2 plus 2 2's 4, 4 to 8, 8 v0 square. So I'll have this is 8gx. So gx into 1 minus 8 mu is equal to 10 v0 square by, sorry, 17 v0 square by 2. I've got everything except mu. All right. So think about it. Have you understood this one?
yes, sir.
అర్థమైందా అందరికి? Or
Yes,
should I go
sir.
for a simpler case first? So if you don't have just got a block and a pulley like this, ఇది ఎంత కిందకు వస్తుంది అంతే రైట్కి వెళ్తుంది. ఇది V0 తో కిందకు వస్తే అది V0 తో రైట్కి వెళ్తుంది. ఓన్లీ డిఫరెన్స్ ఓవర్ హియర్ ఇస్ ద కన్స్టెంట్ ఈక్వేషన్ ఇస్ డిఫరెంట్. ఎవ్రీథింగ్ ఎల్స్ ఇస్ సేమ్. కైనెటిక్ ఎనర్జీస్ ఆర్ డిఫరెంట్. ఇక్కడ కైనెటిక్ ఎనర్జీ కన్స్టెంట్ రిలేషన్ ఫర్ వెలాసిటీ ఇస్ సేమ్ V0 అండ్ V0. ఇక్కడ V0 ఇంటూ V0 ఉంటుంది. ఇది V0 ఉంటుంది, అది 2V0 ఉంటుంది. ఆల్రైట్, దట్స్ ఓన్లీ డిఫరెన్స్ హియర్. ఆల్రైట్,
Yes, sir.
is it clear or do you have any doubt in this problem? Okay, let's do one more. Completely there is friction. All right, neglect this bend. There's a smooth bend here. Particle doesn't collide and bounce there. There's a smooth bend there. Neglect that part, small part. There's a block coming down from here, slipping down from here. I have to determine the compression in the spring. I have to ultimately determine the compression in the spring. How do I do it? Initial energy and final energy are equate. And there is a loss over here, or work done by all the forces is equal to change in kinetic energy. Or I can say initial total energy is equal to initial total final energy. Total initial energy is equal to total final energy. Let's do that way. So I have mgh minus loss mu mgx naught, mu mgx naught. Why am I writing directly x naught? Because from here to here it is x naught. My loss due to friction depends only on the horizontal displacement. It doesn't depend on this incline, that we know, right? It's equal to half k naught delta x naught square. That is required is delta x naught. Alright, I'll not solve it further. అర్థమైంది అందరికి? mgh naught is the draw initial potential energy minus the loss is this much, then final is okay. One thing, there is no friction beyond this one. It is frictionless. Otherwise you'll have to consider that as well. Delta x naught దగ్గర కూడా consider చేయాల్సి వస్తుంది. Alright, so that's next step. This is frictionless. ఇక్కడ friction coefficient mu ఉంది, but here its friction coefficient is 0. So what happens eventually, it will get compressed, again bounce back with the same speed. A speed to ఇక్కడ వస్తుంది, మళ్ళీ వచ్చేస్తుంది. But for the spring to get compressed, how much should be the, what should be the condition? My mgh naught should be minus the loss, minus mu mgh naught should be greater than 0. Only then I'll have some energy over here. After this loss, there should be some energy remaining. Initial mgh naught ఉంది, after the loss there should be some energy remaining. ఇక్కడ వచ్చినప్పుడు mgh initial energy ఉంది, loss minus mu mgh naught ఉంది, దాని తర్వాత కూడా అంత లాస్ తర్వాత కూడా ఇక్కడ ఏదో ఎనర్జీ మిగిలాలి. Only then we'll go ahead and compress the spring. So for the spring to be compressed, this is the condition first. After this condition, I'll have this equation to get delta x naught. Alright, ఈ కండిషన్ ఇక్కడ నుంచి కూడా చెప్పొచ్చు, because this right hand side is greater than 0, so this has to be greater than 0 for this to have a real root. Delta x naught square కాబట్టి under root of this one, so this radicand should be greater than 0. Alright, that's mathematical aspect. But what is happening physically is mgh naught energy ఉంది, లాస్ ఇంత అయింది, ఆ లాస్ తర్వాత కూడా some energy should be remaining to the particle, with the particle as kinetic energy. That kinetic energy is getting further converted to potential energy of the spring. Alright, any doubts over here, students?
No, sir.
And students have corrected some problems for 2 hours class. I told you I'll take a 2 hours class, all of difficult problems. So we are just doing simple problems now. We'll be doing some difficult problems in a session where only MPC students are available. All right, so that NEET students don't feel it waste of time. In the NEET level, mains level only. All the concepts are same, and the level is the questions level same. ఆ level ఉంటుంది NEET లో కూడా. All right, just NEET level itself. But for advanced level, we'll have a separate class, separate 2 hour class soon. All right, within few days, we'll have a separate 2 hour class. Once we are approaching the end of the chapter, then we'll have a lot of problems to do. So we'll do based on work energy itself. I'll do some problems before previous chapter as well, covering previous chapter as well. But focus will be on work energy and power. All right, students, let's stop here. You've got a math class now. Join the next session.